So, in the last class, at the end of the class, I tried to bring out the implications of frequency dependence of the operation amplifier and what it means in terms of the behavior of an ideal operation amplifier circuit vis-a-vis the practical operation amplifier circuit. As an example, I took up voltage follower and I asked you to derive those four relationships of input impedance, output impedance and the voltage gain and so on and so forth. I hope you have done this at home. Appears you have not done it. So, you prove it, take it as an assignment problem, and in the assignment problem I also have given the integrator. When you put a operational amplifier circuit including the frequency dependence, how does an integrator behave, and the difference between an ideal case and a practical case. You will be able to understand this better when you do these two problems. Okay. Today we will take up I have said in the earlier class that an amplifier by definition must have a power gain. But we did not say what is the level of the power at the output. Microwatts or milliwatts or whatever it is, the ratio to output power to input power should be greater than 1. But the level of that could be anything for an amplifier. But those amplifiers which have power levels at the output, a significant value, are known as the power amplifier. Although all amplifiers are power amplifiers, the power amplifier word is reserved for those amplifiers where the output power is supposed to be a significant amount. It may be watt, 10 watts, kilowatts or whatever it is. We won't call a power amplifier when you have output like something like milliwatt or something. We may still call them power amplifiers in very high frequencies, but generally we don't call them as power amplifiers. So, the important thing is power level. At the output. Where does this high power level comes out at the output? At expense of what? Because if you have any amplifier, there is an input and an output. By itself, the output cannot be increased with respect to the input, especially into significant levels. This power comes from these two power supplies that we feed to the amplifier, DC power supplies. So, basically the power amplifier converts the DC power into a useful power at the output, and the useful power is in relation to the input power. But the excess power here at the output comes from the DC sources that are connected. Because the power levels here are very high, as we have started with, then I am interested in knowing what is the efficiency of this amplifier. The efficiency is how well have I used the DC power supply in increasing the power levels at the output corresponding to the input, and am I able to do it 100% efficiency, or what is the kind of efficiency I am able to get. And so, the measure of this power amplifier basically is the efficiency which is the P out. This is the AC power, varying power, as the signal dependent power, divided by P in, which is basically DC power. So, how well I have used my DC power to convert it into the signal power. This ratio is what is known as the efficiency of a power amplifier, and ideally we want eta to be close to 100%. ideally. What kind of circuits will provide you this kind of power gains of the levels with efficiency like close to 100%? So that is the question. Now, in doing this, obviously there is inside here a active device. This active device is the one which converts the DC into high power corresponding to input. So there is an active device inside, transistor, FET, whatever it is. This active power carries some voltage across this and a current through this. So now if you treat it as a two-terminal device, there is a voltage across it and current going through this. So there is a dissipation inside. So this power which is going into this is converted to heat. Since this getting heated up, then there will be transistor behavior will change, right? Because as temperature goes up, the devices will get heated up. So the transistor parameters will change and so on and so forth. So I need to also define what is the amount of dissipation, P dissipation, in the active devices that are sitting inside the triangle here. And we want this to be as low as possible, right? It will automatically be low when this efficiency is high, right? Because whatever P input minus P output, remaining is going into the devices as heat. So the devices dissipation will decrease if I can make this efficiency higher and higher. Was that point clear? So these are two issues. One is the dissipation of the device, and the second is what is the efficiency of the conversion of the DC power into signal power. And this is, I am worried about it because of the level of it. This I am not bothered about a milliwatt level or microwatt level, the efficiency is not important to me. Because I still draw some DC power, but the DC power is so small, it does not bother me. But when you come to power amplifiers, where by definition the levels of the output are high, watts and 10 watts and 100 watts and so on and so forth, I must know how efficiently this circuit has converted the DC power into signal power. Okay? So there are two considerations: to minimize the dissipation, maximize the efficiency. In doing this, there are some definitions. Let us take a sine wave, 0 to 2 pi. If the amplifier input is a sine wave, and obviously output also has to be sine wave, because otherwise there will be distortion. So this is also a sine wave, but this device here sitting inside may conduct for the full sine wave or only for part of the sine wave. I can have a design where the transistor here or the active device here is made to conduct only for a part of the cycle or full cycle. If I allow this to conduct for the full cycle, we call this as class A amplifiers. In class A amplifier, the device voltages and currents are full sine waves, okay, for a signal of a input as a sine wave. For class B amplifier, the device will only have currents and voltages for half the cycle. It is only for 180 degrees, that is either this half or this half, not for the full sine wave. Such circuits which will have devices only having currents for half cycle are known as class B circuits. You may also design amplifiers with class C, where the conduction angle is only this much, less than even 180 degrees, a small amount of, that means the currents and voltages here is only for a short duration corresponding to this angle. Then these are called class C amplifiers. Then we have a class D amplifiers, where historically we had only class A, B, C, but class D is comparatively a recent addition to this class, where the devices operate either in a cutoff mode or a fully saturated mode. In this situation, the device is fully cut off or saturated. You understand this word cut off and saturated? Cut off means there is no current, another condition is a cut off, and saturated means there is voltage across that is 0 approximately.